At its physical core, a computer is just a massive collection of microscopic electrical circuits. Those circuits only understand two states. Electricity is flowing, or it isn't. On or off. 1 or 0. So if the hardware can only process ones and zeros, how does it display a vibrant, high-definition photograph or play back a complex musical symphony? The answer relies on strict mathematical translation. Every single piece of real-world analog data has to be mapped to a specific binary number before the machine can do anything with it. Digitizing different types of data requires 3 distinct mapping systems, one for text characters, another for 2-dimensional grids, and a third for sound waves over time. This table shows the American Standard Code for Information Interchange, or ASCII. It is a simple one-dimensional lookup table. It maps 128 standard English letters, numbers, and control commands directly to a unique 7-bit binary code. But there is a strict mathematical limit here. Even extended 8-bit ASCII maxes out at 256 combinations. It can wedge in a rigid set of symbols, but it completely runs out of room to represent non-Western languages like Arabic or Chinese. Now, look at this massive grid. This is Unicode. By expanding the available code up to as many as 32 bits per character, the system creates enough binary combinations to support every written language in the world. Text is ultimately a direct character-to-number map, but capturing light and sound requires a completely different mathematical approach. To capture a visual, a computer drops a 2-dimensional grid over a picture. It breaks the entire image down into individual uniform squares called pixels. The total number of these squares is the image resolution. Every single pixel has to be assigned a color. Color depth is the term for how the computer allocates a specific number of bits to represent the exact shade of that one square. To figure out how much storage space an image will take up, you multiply those two concepts together. The image file size formula is image resolution in pixels multiplied by color depth in bits. Let's calculate one together. First, we find the total pixels. Multiply the horizontal and vertical dimensions, say 1024 by 1080. That gives us 1,105,920 total pixels. Next, we multiply that pixel count by our color depth. Let's use 32 bits. That gives us our total bits. Since there are 8 bits in a byte, we divide that massive number by 8, giving us 4,423,680 bytes. This math maps directly to physical hardware constraints. Pushing for sharper image resolutions and richer color depths forces the computer to process millions of additional bits, which rapidly increases storage requirements. Natural sound is a continuous, flowing analog wave. To digitize this, the computer has to take snapshots or samples of the wave at regular, distinct time intervals. The number of slices taken every second is the sample rate, measured in hertz. The number of bits used to record the exact amplitude or height of each individual slice is the sampling resolution. The formula for sound file size is sample rate times sampling resolution times the length of the track in seconds. Pause the video now. Try calculating the total bits for a 60-second, 44,100 Hz, 16-bit stereo audio file. Here is how it breaks down. Multiply the rate of 44,100, the 16-bit resolution, and the 60 seconds. That gets you 42,336,000 bits. But watch out for this common trap. The prompt specified stereo audio. That means you need 2 separate channels of sound, so you must multiply your final total by 2. Whether you are mapping 2-dimensional space for an image or chopping up continuous time for an audio track, data digitization fundamentally relies on multiplying grid size by bit depth. When calculating file sizes, pay close attention to the requested units. To convert bytes into megabytes, or MIB, the total must be divided by 1024 twice. Do not just divide by 1,000. To keep these massive files manageable, computers use compression. Lossy compression permanently deletes redundant data to save space, which is how an MP3 works. Lossless compression mathematically packs the data so that the exact original file can be perfectly restored later. Precise terminology is vital for this topic. You must use the exact definitions for technical terms like sampling rate, sampling resolution, and color depth. Accurate unit conversions and a firm grasp of these calculation steps are the primary requirements for this section of the syllabus.